Energy and braking distance. Triple physics only. A moving car has kinetic energy. To slow the car down, work must be done on the car by the brakes. Since work done equals force times by distance, this means to slow the car down, you must apply a force to the car over a certain distance. To slow the car down so it completely stops means the amount of work done by the brakes must equal the car's initial store of kinetic energy. Initial kinetic energy of the car at the start equals the work done by the brakes. Half times by mass times by velocity squared equals force times by distance. If the car is 1,000 kilograms and it's moving at 20 meters a second, its kinetic energy is 200,000 joules. If the driver applies 5,000 newtons of braking force, we can rearrange the equation to calculate how far the car will travel under the braking force. In other words, we'll be able to calculate the braking distance. The braking distance in this example is 40 meters. Please note, if you wanted to work out the total stopping distance, not just the braking distance, you'd have to calculate what the thinking distance would be and add it to the braking distance. For example, thinking distance equals speed times by reaction time. The typical reaction time is 1/4 of a second. So in this case, the speed is 20 meters per second and multiply that by 0.25 seconds. So that comes out as 5 meters. Add that to the 40 meters braking distance to make 45 meters of total stopping distance. When the brakes are pressed, the car's kinetic energy store gets converted into a heat energy store in the brakes and the car slows down. Eventually, the heat energy in the brakes dissipates or transfers to the surroundings and the brakes cool down. Here's another example. If a 1,000 kilogram car travelling at 20 meters per second is brought to a stop by a force of 4,000 newtons, how long was the braking distance? Just like before, we'll start by working out the kinetic energy. Kinetic energy equals 1/2 mv squared, so that equals 1/2 times by 1,000 kilograms times by 20 squared, which is 1/2 times by 1,000 times by 400, which equals 200,000 joules, the same as before. If the car is going to be brought to a complete stop, the brakes need to do 200,000 joules worth of work. Work done equals force times by distance. Rearrange that to get the distance. So the distance will be the work done divided by the force, which is 200,000 joules divided by 4,000 newtons, which equals 50 meters. We can see that the braking distance is longer than before. This makes sense because even though the car has the same size mass and velocity as before, the driver used less braking force. So it was obviously going to take a longer distance to stop. Here's the last example. A car of mass 1,000 kilograms has 3,000 newtons of force applied by the brakes, and the car comes to a stop in 20 meters. That's the braking distance. What speed was the car initially travelling at? First, we need to calculate the work done by the brakes, because we know that's equal to the kinetic energy the car initially had. So the kinetic energy at the start equals the work done at the end. That's 1/2 mv squared is equal to force times by distance. So that equals 3,000 newtons times by 20 meters, which is 60,000 joules. If we multiply both sides by 2, we get mv squared equals 2 times by 60,000 joules, which is 120,000 joules. We know the car's mass is 1,000 kilograms. So 1,000 kilograms times by v squared is going to equal 120,000 joules. Divide both sides by 1,000, so v squared equals 120,000 divided by 1,000, so v squared is 120. If we square root both sides, we'll work out what V is. So V is the square root of 120, which equals 10.95 metres per second. Here's some questions for you to try. Pause the video and give them a whirl. And here's the answers. Well, I hope that helps. Smash that like button and subscribe to the channel, thanks. Work hard, be nice, stay safe, and bye for now.